the idea of this talk is formal methods. Has anybody done this, had any classes, or done any work in formal modeling? A couple of hands. So, goal is to actually formally prove that what you've done works, or works as intended. We're gonna explore that space. We're not gonna go all the way into it, but that's kind of the goal of this concept, this talk, is to teach you some ideas around formal modeling and formal methods as applied to security. We're gonna go like this deep. There's a lifetime of learning that's involved in making this really work, and dozens and dozens of years of effort to make even the simplest things formally prove it. So we're gonna scratch the surface, but I want to show you kind of some techniques that you can take away that are kind of steps away from real formal proofs that also kind of fall in that space of formal modeling that can help verify programs and verify systems. So there's a couple categories that matter here. The kind of lowest level of formal modeling or formal methods is specification, right? Just simply having a specification is still a formal method. It's not executable, it's not verifiable, but it is actually a formal specification. Lowest level of formal modeling is just that. If you think about crypto systems, which we'll talk about shortly, there's an algorithm that you can specify as really the specification for the crypto algorithm, right? So the base level is just that specification. It's just math in the case of crypto, but when you think about if you ever written a spec for something, it's there. RFCs can become specs as well. There's some talk on whether or not that's true or not, but you can use those as kind of basis, and that's the lowest level. Then there's development. Once you start to actually implement a spec, you have things you can do during the implementation phase of a specification. Things as simple as a type system still count as formal methods. A compiler can formally prove that the types are correct. Some languages better than others, and we'll get into some of that as well. But that's kind of the next game. And then finally, there's verification. This is where we get SMT solvers and theorem provers and actual real formal mathematics behind what's going on. We're going to talk about all of these, but probably in varying degrees of detail. I'm going to go heavier on the specification and development side, and I'm going to touch the verification side. But I'm going to give you some references on things that really actually spent, dozens of man-years doing this. We're going to skip a ton of basics. I'm around afterwards to talk. I'm just going to sail through a bunch of stuff and assume we all know it, which I know isn't true, but I want to get you guys something to walk away with, and then to kind of research on your own later. A bunch of the stuff you probably have never seen before. I saw one hand, so maybe it might be familiar, but some of this stuff is maybe not seen before. Totally okay. Don't worry about it. I'm going to give you some references and some things to go read later. So if you like this and you want to read more, a whole bunch of stuff for you to read later. Before we start, we have to talk about why you want to do this. Tons of effort goes into doing this. This is not something you take lightly. You have to have a reason to do this. If you don't have a reason to do this, don't do it. It will cost you your job most likely. But we'll start with a threat model, right? If we're gonna do anything in security, let's start with a threat model. One of my favorite ones, which ends in you'll be massaged upon. And there's really no hope. But this is actually important, right? Before we justify doing this work, we really want to start and figure out what we're protecting against, right? If we're going to protect against something that doesn't really matter, then, maybe a bunch of formal verification isn't in our wheelhouse. But if we're going to protect against, nation states, real adversarial attack, and we really have to be sure, the formal methods actually matter. And I'll talk about a project shortly that did that. And that was their adversary. So sometimes it actually is worth doing the work. The project I'm talking about now is called HACMS. Has anybody ever seen or read about the HACMS projects from DARPA? Really, really cool. You should absolutely watch their video. They took some drones, and they gave them to their red team, and they, of course, destroyed them, took control of them in various sorts of ways. It took them just a few minutes. And they re-implemented the OS for the drone, and a formally verified runtime kernel. And then they gave it back to the red team, and gave them access, and they gave them everything. They couldn't touch it. And then they moved this into the Boeing unmanned aerial drones and had the same success, right? So when you're talking about that level of assurance and that level of safety and criticality, this stuff actually does apply. Now, most of us in the room probably aren't going to go that deep, but this is an awesome example of applied formal methods. We're going to talk about crypto for a minute, for a couple of reasons. One is that crypto is really small, compact, and precise, right? It's specified. So you can start with a working spec and not have to make one up. And we're going to do really rinky-dink nonsense crypto. So it'll be really, really easy to kind of dive into. Before we start, some languages are better at modeling than others. So when it comes to implementing crypto, there's kind of one language that people usually go to. What is it? What does most of the crypto people use implemented in? C. Yeah. C is, for lots of reasons, one of the best languages to use to implement crypto. It's also one of the worst languages in the world to model crypto, because of all the stuff you do in between: memory management, the manipulation, the things you do against constant time comparison, and all the stuff to get it right. There's a bunch of implementation details that actually don't matter at all to the model of what the crypto should look like when it comes out the other side. So you can actually take your implementation language and your modeling language and separate them. What you end up doing is creating a nice, loose, easy to read, implementation-specific free model, and then all the way down to the meat and potatoes implementation, and you compare the two, and you start to figure out whether or not they deviate. So what we're going to see here is we can do both. We can use both, and we can actually do formal modeling based on this model and the implementation, and we'll go through that exercise. So I don't have to warn this crowd. Sometimes I give this to developers, straight developers, and you have to wonder sometimes. But this is not suitable crypto. You should not use this at work. Please don't. We're going to do the C cipher. I'm going to do this because it really is one of the simplest things to implement. It's a simple shift. Very easy to model, very easy to implement. And the good news is it fits on a slide. That's kind of the bonus thing for this talk. I don't have to do multiple slides. But if I wanted to take a C cipher and actually make sure it was correct, there's a bunch of things I can do, right? I can write tests for it, of course, but if I really want to go further, I really have to kind of dive in. So like I said, models and implementation. I'm going to start with the model. This model is written in a language called Haskell. Anybody seen Haskell before? One. Okay, cool. So don't worry about it. I'll explain the basics. Everything in Haskell, well, not everything, but in most cases, we'll start with the type signature, which is the name of the function, the types, the input types that it takes, and the output type that it returns. In this case, it takes an integer, which is the shift, the string, which is the message, and it returns the ciphertext. When we're given the input, we go across every character. We make sure that it's in the range of the uppercase English alphabet, which is our constraint. It's very important when you model something to make sure you're constraining it to the real world. Whenever you don't properly constrain a model, formal verification gets very difficult. So you want to constrain. In this case, we're going to say uppercase A to uppercase Z is what we care about. We're going to take the integer values of those characters and do the mod 26, which is part of the algorithm of the C cipher. If it's not in that, we'll just kind of return the character as part of the string. That's the model. That's C cipher. That's the whole thing, right? So regardless of whether or not you're proficient in Haskell, it's really kind of one line of code for the essence of it. Now, we can have an implementation. So we do this in C. Our C code is buggy for various reasons. If you are familiar with C, you'll spot it. You may spot it quickly. You may not. But you'll see that there's some bugs in here. The presence of some functions here will probably alert you immediately if you're used to looking at code that there's issues here. But can anybody spot one of the half dozen bugs in here? Yeah, it was not terminated. Yep, that's a big one. All right. Well, I'm not going to tell you. We'll leave it to the surprise for a little bit. But we want to know how to compare them, right? So I have a model in Haskell. I have a thing in C. How do I figure out whether they're equal? And how do I do it efficiently? We're going to write property-based tests, which effectively are their own kind of models in and of themselves. I won't get into what property-based testing is, but I'll actually just show you a couple of them so you can see. What I can do is state an equivalence property that, my Caesar function that I wrote in Haskell is the same as the C function. The problem is the C function is not in Haskell, so we have to get it there first. We have to be able to test both pieces of code in the same environment. So we can actually use Haskell's foreign function interface that calls shared objects in C. We can reach right out to the compiled object, run them both inside the Haskell environment. So we can wrap our C code in a bunch of Haskell. Again, if you're not Haskell familiar, no big deal. What this is doing here is importing the symbolic, importing the symbols from the compiled C code from a header file, using the types C int, C string, and returning C string. When you use foreign function interfaces, so C code, Haskell code, strings in Haskell are not strings in C or characterized in C, so there's some conversion you have to do. That's just type checking to make sure that the types are represented properly under the hood. And then our native Caesar function is our wrapper. Again, it's a type thing. When I talked about type systems being part of the formal specification, part of formal modeling, Haskell's type system can do that kind of work, right? C's types and Java's types, okay, they do some okay stuff. But when you get into a type system that really is after correctness, Haskell's type system has a lot more to do with this. And you'll see something called IO string later. I'm not going to talk about monads and any of the fun stuff there. Not relevant to this talk whatsoever. But what this is doing is kind of wrapping the C code and making sure all the munging and internal manipulation is done for you. So we can just talk about it in terms of pure Haskell, which is what we're going to do on the outside. So we can fire up our environments for Haskell and actually call both pieces of code. So the first one is the Haskell code, giving it a shift of 2 and a plain text attack at dawn. And then the native Caesar code, which calls the C code, and a shift of 2 and the same text. And we can see that they're equivalent, right? So I've done the basic test. I ran the 2 in the same environment, and they gave me the same answer. So yay, right? That's cool. Now we have some stuff to address. So if we want to run this in a test, we actually have to go all the way through and make sure it runs all the way through a test suite. So we go to native Caesar code. We have our regular Caesar code. We have to fix the types for Haskell to work. I'm going to skip by this, because it's probably not relevant for right now. We end up with a property. Our property says that for any input that I generate, the output of calling one of these two or both of these functions with the same shift and the same string should give me the same message, right? Telling me that the cipher text is the same in both cases, which is effectively telling me that it's the same thing, right? I have no discrepancies. So if I run this, I should see no discrepancies. That's my statement. GenSafe string is a generator that constrains the scope down to just uppercase A to Z. So it's making sure that the inputs are satisfied just like that. That's the constraint I'm going to work with to start. I'll skip by that. That's more just some specification of the generator. So we could run some tests using a quick check property inside of Haskell, and it would say, yeah, we're all good. What I want to show you then is what happens if we run that with our current buggy code. So right now what I have is a failure. 29 tests in, this string, whatever, this plain text produced a different value in both cases. So what I would do is say, call my Caesar function with a shift of 2, and I grab that input. And I see this, and then if I want to do this again, call my native Caesar code. And something is going on here. It may not be obvious, but there's definitely a discrepancy here. Yep, you got it. Something in the memory. It's dumping out memory. Now, sometimes when I do this, it's great because you'll see like a file path show up or something that's obviously memory resident. But in here, what we're seeing here is a memory issue being exposed in our test suite. So without really digging into the code or understanding it, we could expose things like a memory issue. This is just scratching the surface. But again, what that lets us do is run back, fix our code, and keep going, right? So we can go back to our model. I'll do the cheating way, which doesn't actually fix all the bugs, but fixes the general bounce check. If we did that, it'll fix the overrun in the for loop. I could recompile it. Start up my environment. And then everything works again, right? So what I'm seeing is a rapid development pace, right? So if you're looking at this, I can just quickly do this without writing code to make sure that things are not breaking underneath me. But I'm not running one test. I'm running a whole bunch of tests with generated input. So what I'm really doing is kind of fuzz testing my code. In a roundabout way, but I'm fuzz testing with a purpose and a focus, and concrete statements of what should happen, right? For all, or things that you can actually put into a mathematical equation, right? And a real property. So we can also turn the heat up, right? We can say run it 10,000 times, run it 1,000,000 times, run it 1,000,000,000 times, run it for 2 weeks, run it for a year, right? You can do this however you want to. You can control the knobs here. You can turn it until you're satisfied. But the question then becomes kind of the Rice's theorem problem of how much is enough for black box testing, right? Like when do we say stop? When are we confident? When does it actually work? we haven't formally proven anything. All we've done is build confidence. So we've been able to verify things and build confidence, but QuickCheck doesn't actually get us all the way to satisfying, right? It says, oh yeah, I can be super confident this works. It's way better than a single unit test. But I'm not actually confident that it's really, really accurate yet. Also, there was a whole lot of work, right? We did a whole bunch of work for really not much reward, right? We found a bug in C that we probably could have spotted just by looking at it. So in some cases, it's better than others because in some cases, of course, it's a ton of code and you really can't see all the bugs, right? It doesn't fit in the slide. It's a huge thing. This kind of testing actually gets you a long way. So I don't recommend, just kind of disregarding it. It's really cool. But in this case, it's a lot of work for a little reward. So there's better ways to approach this. I'm going to start with the modeling side, and then I'll go on the implementation side, and we'll meet back in the middle again. The first in the area of crypto is a thing called CRYPTOL. It's a language. There's a company out there called Gawa that does a bunch of research for military and other applications. And they created this language that's a language specifically created for specifying cryptographic algorithms and testing them. A really, really cool project. So I'm going to start with examples, and then we'll work into crypto. You'll see some things that are similar to Haskell in here, because that's what it's built with. But you start to create, like I had before, properties. Underneath, though, when you actually run the property, you can call something, there's check, which is the quick check, and then there's prove, which actually has an SMT solver underneath it. You really are formally proving that something works. So there's a classification of tools called SMT solvers, there's SAT solvers, theorem provers. All of those exist within the context of CRYPTOL. And you can run them on your code and actually have them return, well, if you model right, they'll return. If you model wrong, they'll never return. But in this case, it's very simple to see, and we see when we prove, we get the QED out the other side, which means I've formally proven that these two functions are equivalent. Now, that was easy to prove, of course. So we can then take a step further and model our Caesar cipher in CRYPTOL. So then what we could do is, go through exact same thing that we had before. It's going to be spoken a bit differently because CRYPTOL is a different language. But we can then do our simple model we had before, where we open up the environment, call our Caesar function with a shift of 2 and the same message, and of course we get the same answer we had before. We can take it a step further, though. Because how do we know the model's right? We can make better models because with the SMT solver, we can really formally prove them. So we can write the reverse. We can write the D Caesar versus the Caesar. We can run it backwards and forwards, and actually then formally prove that our model is correct. So now we start with a working, formally proven model that we know is good on the outside. So then we use that to test our implementation. We have something that we know is right. Because if you ever have a test and one thing disagrees or both disagrees, at least one of them is wrong. So if you can prove that at least one of them is right no matter what, you know which one's wrong. Because that's the hard part about a test when it fails. You don't know which side of it's wrong. Or maybe you had a test that ended up being a broken test, not a broken implementation. You should all be raising your hands right now because you have. It always happens, right? This is a really common thing. So knowing that one side of this is always right is really, really powerful for testing later. So CRYPTOL gives us a better way to model. And it gives us a way to prove that our models are correct. So that's one side of the equation. But we lost all the interop that we just had with the environment we used before, because CRYPTOL doesn't have a foreign function interface, and rightfully so. It's about modeling. So there's a tool also created by Gawa, which includes CRYPTOL in its army of tools called SAW, or the Software Analysis Workbench. It's a formal verification tool for C, Java, and CRYPTOL. So it includes CRYPTOL in its mix. So I'm going to start with a couple of basic code examples that have nothing to do with security or crypto. We're going to find some bugs. So I have a basic example in C. I have a reference in C that we know works, which is adding two numbers together. And then I have an add with a bug, where if x is equal to 5, I'm going to return 42. I'm going to compile that, but instead of compiling it outright, I'm going to compile the bytecode. More modern C compilers have multiple options. There's the machine code you compile to. You can also compile something called bytecode, which is for an executor on the back end. CLang and LLVM are the targets there. We can then use SAW, that's really a scripting language, to analyze this and extract the bytecode, find the functions, and then run them against proofs or theorems that we developed. Right? In this case, what I'm saying again is an equivalence theorem. We also introduced the idea of SAT searching. So satisfiability and theorem proving are two different ends of the spectrum when you're looking for formal verification. one or the other could be faster based on how you specify the theorem. So the different tools have different speeds at which they can identify bugs or problems. So one approach is that I can say, a stat search will say, find me a value where this is true, right? Whereas what I'm saying is, I have a theorem, given an x and a y, that the reference and the bug don't equal each other. So tell me which value that is, right? And so you're getting to a point a different way. With the theorem for the failed proof, I'm going to say that they're equivalent, prove me wrong, right? We're stating the problem slightly differently, and the tools that are created around there might find the answer a different way. In this case, it's pretty simple. When you have more complex models and more complex equations, how you say it matters a lot. And it's the difference between your proof returning in a couple of minutes or never returning at all. Or maybe your proof returning in an hour or two or a month. Right? So how you state it and how the tools analyze and optimize for the equation really matters. But if we run this, we'll see right away that the stat search and the failed proof both show with an x of 5, I get this bad value. So again, finding bugs without actually specifying anything other than I expect these things to behave this way. So, for the fun of it, we'll do the same thing in Java. I'll use x of 7 versus x of 5 so we see which one's wrong. Same exact idea, same exact bug. We'll compile it with the Java compiler, just normal up, because Java compiler will emit bytecode regardless. Again, we'll use saw to load in the bytecode and extract the terms. And this time we'll say we have a C reference and a Java bug, a Java reference and a C bug, and in both these cases we'll use the theorem prover. And when we run it, it'll show us our Java bug and our C bug right away, just by defining a property. And so what we've done then is specify what should happen, not how you should go about testing it. This idea is really important. A lot of us, when we're testing, get caught up in the implementation details of a test, right? We say, oh, if we do this, and we do this, and we do this, then this result happens. And sometimes that's great, and sometimes it gets you back to the point, and sometimes it actually leads to a bug that nobody else can reproduce, right? So when you end up in these situations where you're defining a behavior that should happen, you usually find something you can always reproduce. Kind of like you found in that quick check example. So what this gives us now is a modeling language that works a little bit better and can be formally proven, and an interop system that we can use that actually pulls things in quickly, right? I didn't write wrappers, I didn't write type conversions, I didn't do all that stuff I had to do in the Haskell example originally. I just said, pull it in, and go ahead and just analyze it, right? I skipped that entire step. Now, I was a little bit unfair to Haskell because there are some tools that do FFI automatically for you, but they're still kind of a pain. Like, this does it automatically. So now we have a more suitable example. We can actually start with something that means something to us. So this is a CRYPTOL reference for AES, right? This is not the entire CRYPTOL code. This is the part that matters, right? This is encrypt and decrypt, right? The S boxes and the key expansion and the other things that make the algorithm work are not on this slide because they won't fit on this slide. But this is the meat. This is where the real specification of AES comes in. This has been formally proven. It's part of the CRYPTOL suite. You can go in the examples and see it. This is not my own writing. It was what Galois did. But what's more important here is that what we have here is something we can prove. You can also take a C implementation, which will not fit in the slide at all. I tried. There's just no way to do that. So we'll pretend we have a C implementation. I have it sitting on my computer if you want to see it. And then what we do is we start finding where implementation fails. I have a different method here that I'm using. In crypto, especially in AES, it's one of the easiest ones to look through this on. It's a finite state machine. That's all this is, right? You have a key, and you have a number of times to expand the key, and you have a final state. So when you have a state machine like this, it's deterministic. So what we're talking about is a network graph. When you have how many of you ever did hardware back in the day? Any hardware stuff? Anybody ever do logic synthesis for when I say hardware, I mean developing hardware, actually developing circuitry. Did you ever use logic synthesis tools to test your hardware before it went to production? So it simulated the gates, the interactions, because you had a finite state machine in your hardware. And so basically what you do is use logic synthesis tools to make sure the circuitry that you designed was actually correct before you shipped it out and made a bug, right? That same idea of logic synthesis for hardware, especially when you have a finite state machine, applies here too. We can actually create a representation of a network of a finite state machine underneath this implementation because it is. So what we're doing is we can use the tools underneath. So the synthesis, ABC is the synthesis tool that it uses underneath to generate a sequence of bits that define the network for the AES state machine. So we can do that with our Haskell code. There are state machines that are already published for AES. So you can take the published version of the state machine, the model version of the state machine, generate one for your code, and see if they're equivalent. So you're doing just network searching. At this point, it's not theorem proving or stat solving, or SMT solving, I'm sorry. It's just simple model finding. Network equivalence. You're saying, is this network equal this network? And if it doesn't, you have a problem. And when you run it, the C implementation happened to have a bug, and it said this input value just didn't work. I tried to encrypt it and it didn't work. Didn't round trip. In this implementation, there was SBox problems, and that's what caused it not to round trip. But it gave you a concrete implementation. You could walk it through a sequence and go, oh, this is what happened, and you can debug it. But what you saw was that the crypto didn't match up. This is tough, right? Because if you look at two encrypted strings, they're going to look encrypted, right? I mean, more or less, unless you're using ECB mode, stuff, and you see the penguin. But most of the time, you're going to see encrypted garbage, and you're not going to know whether or not it's right or correct. There's two implications here. One is, of course, you could mess up data for customers. Two is, if somebody's tampering with your encryption code, somebody's delivered you encryption code that doesn't work, or maybe is backdoored or providing some detail, leaking some detail, you wouldn't know it. If they did it right, at least. You can actually use this kind of tool to find out that they've actually been tampered with it. Or they've just gotten it incorrect, which happens more than you want to believe. So, I made a couple leaps there. In the interest of time, I'm going to skip over and inverter graphs and logic synthesis because it's really, really cool, but I want to talk about some other stuff anyways. So, the next piece, right, I talked about inside out. How do you take an implementation and figure it out? Make sure it's right. The other part of modeling and specification is describing a system and the series of interactions in the system. So outside in. We've beaten the crypto thing to death for now. I'm going to talk about something different, but there's a tool called the Cryptographic Protocol Shapes Analyzer, which is a tool by MITRE that actually looks at the protocol and examines the protocol for inefficiencies and insecurities. So how does protocol exchange work? Now, of course, you can apply it to crypto, but like I said, I'm not going to go down that road. This tool found some bugs that were actually quite old. Needham-Schroeder key exchange protocol had a 19-year-old bug nobody had found, and they ran this tool on it and went, got it. It was real quick. So there's some really cool stuff that happened as a result of this tool being developed. But what I want to talk about now is modeling the world. So I want to model authentication. So in our world of microservices, where everything's a service, and we have 15,000 services doing 15,000 different things, authentication gets a little more difficult because you're sending authentication through a service, and then everything else is getting its stuff. So we'll pretend that we have a centralized auth service, and then we have a couple of HTTP services hanging off the other side over an SSL channel. So I'm going to go through this, and instead of going through the details, I'll talk about the idea. The dialect here is a Lisp dialect or scheme dialect that you describe things in. But we end up describing a protocol. We describe what's our auth service. We describe our services. They're generic. They're just endpoints. So we can reuse the same one for both, right? It's just a call and response kind of thing. But it talks about what's going to happen, right? There's going to be a username and a password. You'll get a token back that's signed. In a service, you'll use an encrypted channel and provide a token to get information. An end user will coordinate all of this, right? They're going to be the ones sending the username and password, receiving the token, sending data over an encrypted channel, getting it back, and so on. Skeletons are basically the idea of execution. What does the execution model look like, right? What I have is a bunch of noise, and then I have an SSL channel and a bunch of data. The SSL channel has a couple of important things. SSL channel is going to have something called a long-term key, or a private key, right? The thing used to sign the certificate, right? That server certificate is quite important, and it matters to this model, because if you don't have it, we'll see what happens. And also the signing key is a long-term key, so it should be considered unknown. What we're doing is creating a model of the world where we hope that nobody has this information. I'll have some fun with it in a minute. Then we have our interactions, which is basically an auth service gets called, a user calls an HTTP service, and so on. Very simple interaction. The most important part, though, right, is we assume that there's a non-originating long-term key, that's the SSL key, and we assume that we have a non-originating private key that we're using to sign the token. Those two pieces of information are very, very important, very critical to the security of our data. And so if we run this, what it's going to do is take the model of the world and find out all possible terminating interactions that could take place. and generate you a bunch of results. Now, this is an image of one of them, right? This is the fully realized version of log in, call one service, call two services. The other possible options are log in, do nothing, log in, call service A, log in, call service B, and the reverse of those two, and then log in and call both services, right? Those are our possible terminating options here. That's the whole thing. But we could comment out the thing that says we have a non-originating long-term key in the SSL channel, right? Once we do that, and we run the model, something different happens. It goes, hey, if I knew that long-term key, I could probably do all kinds of stuff in between those requests, right? It's now telling us, hey, I can get in the middle of this. I mean, it's very obvious that if somebody has your certificate, they're going to be able to man in the middle of you. But what it's doing here is showing you that that's happening, right? As you model this, it shows you that my model was incorrect, and now I have a vulnerability, which is a man-in-the-middle attack, and that's what it manifests itself as. So again, I didn't specify how. I just said the world should behave like this. Tell me what would happen if it did, right? And so this was the first result I got, because I didn't specify that was a non-originating long-term key when I was modeling this. And I went, wait, that doesn't make sense. How could somebody? Oh, I have to say that somebody. I have to really specify in my model that somebody doesn't know that key, because it told me what happened if they do. Right, so this looks obvious, and it certainly is. But when you're thinking about modeling, you have to think about what the consequences are. So the last couple of years in this space, there have been a ton of developments. The HackEms project from DARPA took things quite a ways forward. The tools used to be really, really rough. And in fact, they are still kind of rough. They're academic quality. I would call them that, right? It means that they're research-based. They've solved they had a purpose. They solved that purpose. A bunch of PhDs worked on them. They solved their problem. They left them, right? They didn't commercialize them, right? So commercialization of formal methods, tools is immature, right? In its infancy. But the last couple of years, the tools have improved dramatically. Stuff I showed you is all open source. It's all free. Again, academic quality in most cases, but active, right? People are maintaining it. It's on GitHub. I've sent pull requests off, and they've acknowledged them. The people are still actively maintaining them. So there is hope there. But the tools bring the ideas within reach. Doing this on your own 5-10 years ago would have been considered mostly impossible, right? A bunch of people set out to do it, and the HackEms project proved that you could. They had a success, a big one, right? And then things like the CompCert C compiler they're using for aviation and those kind of tools have come around, and formally verified compilers and other things like that that are actually really helping people get stuff within reach. And the thing to remember is that when you're doing this stuff, you can only formally verify so many things. You can't do the whole thing, right? It's the kernel, it's the compiler, it's the critical components that you formally verify, and everything else kind of goes to the side. Because going all the way down is just years and years and years worth of work for people who just do this every day. I think it was 10 man-years for DARPA HackEms to do the formally verified kernel for the airplane. And it was just the kernel. But the kernel controlled the execution path, which got rid of all the really nasty bugs and takeovers. I promised references. The SAW project, the CRYPTOL project. The LLVM verifier has some interesting stuff, which is the bytecode symbolic extractor. There's a Java one too. But it's really kind of how you extract symbols from bytecode and use them in other contexts, which is kind of how you have that place inside of SAW to compare different languages. So it's a really interesting thing to look at how the technique they use for drawing that stuff out and kind of playing with it and executing it in the same space. And then CPSA. There's really no formal website for it. It's a bunch of papers from MITRE. Again, academic quality. But that's the seminal paper for CPSA. And so I think I've gotten through all 45 minutes, or all 75 minutes in just under 45. So I have 30 minutes left for questions if anybody wants to have questions. Or I'll be happy to talk outside. Yes? Mm-hmm. Yeah, so in the in the CPSA source code, there's a bunch of examples, and you'll see a bunch of the TLS stuff there. You'll also see some of the foundational stuff. You'll see Diffie-Hellman in there. You'll see a bunch of the handshake protocols that are inside of there that are also modeled. So yeah, there's some of that stuff is sitting there as examples for. I'm not sure. I don't remember which ones are in there. I don't remember FIDO being in there, but it very well could be. I've seen the FIDO stuff pop up in a few different of the tools that I talked about here. I don't remember which one it's in and which one it's not, though. Of course. And so now that we have them, we can, right? We can spend the time. So if you're doing research, this is a great place to start. If you're not doing research, it's probably more something you play with in your spare time. Yeah, I mean, these tools are available now, and the work can be done. And there's a little bit of a learning curve to get up to speed on it, but really, it's once you get there, you can do some really cool stuff. Any other questions? Cool, thanks.